Okay. Hello, everyone. Welcome to Analysis Invited Talk at ICM. Thank you for joining us. My name is Benjamin Sauer from University of North Texas. It's an honor to introduce our distinguished speaker, Cyril Houdayer from University of Paris-Saclay. His talk is pre-recorded. Cyril already delivered the talk at the Satellite Conference in Copenhagen a few days ago. But he is live here and also is going to be live on Discord to answer any questions you might have. Please feel free to interact with him there. So without further ado, here's the talk by Cyril Houdayer on non-commutative ergodic theory of higher rank lattices.
Well, it's a great honor for me to be invited to give a talk at the ICM 2022. And also it gives me great pleasure to give my talk here in Copenhagen at the conference on operator algebras, dynamics and groups. And I would like to thank Cyril Houdayer for making this happening. Thank you so much. Let me start with a brief introduction to the topic. So, in the title, there is this notion of higher rank lattices, and I want to explain what I mean by this. So first thing first, one slide on simple algebraic groups. So here, K will be a local field. You can take K to be equal to R if you want. And the letter G, or blackboard bold G, will denote a simple algebraic group. And what I mean by this is that it's connected, it's defined over K, and the important assumption here is that it's almost simple in the sense that the only proper normal algebraic subgroups are finite, hence central because the group is connected. And the other important assumption is that the algebraic group is what we call K isotropic, meaning that it has a non-trivial K split torus. And so the rank of the algebraic group is the dimension of a maximal K-split torus in G. The example to keep in mind here is SLN, okay? So whenever n is greater than or equal to 2, SLN has all the assumptions that I want. And the rank of SLN is n minus 1. So let's keep this example in mind. This is, in any case, my favorite example. And now for the notion of higher rank lattice. So what I will do is fix an index set 1 through D. And for each I will take a nice algebraic group that satisfies all the assumptions that I want. And I'm not so much interested in the algebraic group, but really in the group of its K points. So I take the Ki points of each of these groups, and then I get a locally compact group, which is compactly generated. And then what I will do with this group is take the product group. So G is G1 times G2 times GD. And I say that a subgroup gamma in G is a high rank lattice if it satisfies the following three conditions. So first of all, gamma is a lattice. Okay, so it's a discrete subgroup with a finite covolume. The second assumption is that when I have at least two factors, so when D is greater than or equal to 2, I want my lattice to be with dense projections, in the sense that the projection of gamma into any non-trivial subproduct is dense. Okay, so I do not want my lattice to be a product, of gamma I. So I want to avoid this. And the third assumption is that this is the high rank assumption. I want the sum of the rank to be at least 2. So what does it mean for us? It means that we are in the following two situations. So either D is equal to 1, and then we have a lattice in a simple group. Okay. So here I will just use notation instead of K1, just K, and instead of G1, G. And then I have a simple group with rank greater than or equal to 2. Or I am in this situation where I have at least two factors. And so here I will say that it's a semi-simple or product situation. So the reason why I'm emphasizing this now is because, in fact, in our proofs, and methods of proofs, this distinction actually is important. And conceptually, the proof is different when the group is simple or a product. So I will come back to this a little bit later. So again, taking my favorite example, SLN. So we have some nice examples of high rank lattices. So they are all of arithmetic origin, and it's not a surprise because all high rank lattices are arithmetic. So we have the example, for instance, SLN Z and SLN R for all n greater than or equal to 3. We also have an example in positive characteristic. And for the semi-simple case, so now we allow a product situation. And for instance, for SLNR, we can take 2 copies of SLNR, and then we take a square-free integer, and then we can look at SLNZ root A to be a lattice with dense embeddings into SLNR times SLNR. And so what's interesting to notice here is because now we are in a semi-simple situation, then we can allow lattices in SL2 times SL2. Okay? And the second example is also one I like a lot. It's when you look at SLN Z adjoint S inverse when you have a product of primes. And now we have, it sits as a lattice with dense embeddings in copies of SLNR and then SLN QPs with the various, completions. Right, so keep this example in mind, SLNZ and SLNR, or SLN, say, Z root 2 in SLNR times SLNR. So now what about the motivation for the results I'm about to present? So from now on, when I say gamma in G is a high rank lattice, it means that, that's exactly what I defined before. And the sort of the main motivation and a result that inspired us a lot is Margulis normal subgroup theorem. So for any high rank lattice, whenever you take a normal subgroup, then you have this dichotomy: either the final subgroup is normal, hence central, or it has finite index. So you have this dichotomy between small and versus big. And you see this statement is beautiful. It's completely algebraic in a sense, but the proof is not actually. And Margulis' remarkable strategy goes as follows. Assuming that you have a normal subgroup n that you assume to be infinite, then you want to show that the normal subgroup has finite index. Then it means that you want to show that the quotient group is finite. And then Margulis' idea is the following. To prove that the group gamma mod n is finite, we will show that it has both property T and is amenable. So the property T part uses functional analysis. And I will focus more on the amenability part, because this is the part that we were sort of able to extend in the non-commutative setting. And the proof of the amenability of gamma mod n, it's really ergodic theoretic in a sense. And this follows from this result of Margulis known as the Margulis factor theorem that says the following. So in each of these group GI, you can take a so-called minimal parabolic subgroup. When it's SLN, you just take the group of upper triangular matrices. And you take the product of these groups, so you denote it by P. So P is a co-compact subgroup in G. And Margulis showed, in fact, that any measurable gamma factor of G mod P, it's in fact isomorphic, gamma isomorphic to some G mod Q for unique intermediate closed subgroup Q between P and G. And Q really comes from, it's a product of intermediate parabolic subgroup. So as you can see, any measurable factor of G mod P is really a G factor. So it's gamma isomorphic to G mod Q. So the reason why I'm stating these two results is because in a way we will, I will later on, I will state results that sort of give, non-commutative extension or strengthenings of these two results. So the goals of my talk is, the idea is to use operator algebras, and when I mean operator algebras, I mean both C-star algebras and fundamental algebras to explore new rigidity phenomena for high-rank lattices. And among the things that we want to understand is, given a high-rank lattice, for instance, the dynamics of the group acting on its space of positive definite functions, but also look at the group C-star algebras generated by arbitrary unitary representation, not just the left regular representation. And at the end of my talk, I will make a connection with rigidity conjecture and discuss some rigidity aspects of the group fundamental algebra. And for other, fascinating interactions between high-rank lattices and operator algebras, I advise you to watch Michael de la Salle's talk also at the ICM. So much of this work has been a joint effort over the years. So we started this whole thing with Rémi Boutonnet a few years ago. So the first and the third paper, basically we treat the case when we have a simple group. And the second paper and the last paper, which will appear soon on the archive, we treat the case when we have a product group. So I will explain a little bit later what's the main ingredient in our proof, and I will kind of explain what's going on in the simple case. Okay, so now let me first actually explain in sort of the main applications of our results. And it's about, dynamics of positive definite functions and also character rigidity. And also I will mention a few results in topological dynamics. Okay, so for me, so here for the moment, lambda, it's not a high-rank lattice, it's a countable discrete group. Well, so it's well known, we have the space of positive definite functions. I would like those to be normalized, so they send the identity to 1. So it's a nice weak star compact convex set in L infinity of lambda. And to any positive definite function, so a positive definite function, it's a coefficient of a unitary representation, but there is one there is a favorite one, which is the GNS representation. And so because the group gamma acts on itself by conjugation, then the conjugation of gamma on itself induces an action on the space of positive definite function, and this action is affine. So you really act by precomposition by conjugation. And for this action, what are the fixed points? Well, the fixed points, they are called characters. Okay, so a character, it's a positive definite function, say, who is invariant along conjugacy classes. Sometimes it's called simply a trace, and some authors prefer to use the word character for an extremal trace. It's a matter of taste. I prefer character, so I will use character. And then we can denote by car lambda the convex subset of all characters. So let me give a few examples. So first of all, examples coming from groups, or rather subgroups. So there is this space that is well studied in topological dynamics because of its links with invariant random subgroups and uniformly recurrent subgroups. So this is the space sub lambda of all subgroups of lambda. So it's a compimetrizable space. It's a closed subset of 2 to the gamma, or 2 to the lambda rather here. And again, we have this action by conjugation. Okay? And there is a natural map. So whenever you have a subgroup, H, you can look at its characteristic function, right? And it sends, so this map is equivariant, and it sends, it goes from sub lambda to the set of positive definite functions. And what's interesting with that is that, in particular, if you start from a normal subgroup, then you get a character, right? So the normality translates into invariance along conjugacy classes. And two rather important example, I would say. Well, when the subgroup is whole lambda, of course you get the trivial character, But when the subgroup is the trivial subgroup, then you get the Dirac mass at the identity, which is called the regular character. Okay, and so you see that the corresponding GNS representation is the so-called quasi-regular representation. So this is one example of characters coming from subgroups. There is another one coming from ergodic theory. So whenever you have a probability measure preserving action of a group lambda on a space X nu, then you can look simply at the map that sends an element gamma to the measure of fixed point. So you can show that this map is indeed a character. So you need to see it as a coefficient of a unitary representation. One way to do it is to look at the equivalence relation to do that. And you see that this character being the Dirac mass at the identity means exactly that the group acts without any fixed point, almost everywhere. So we say that the action is essentially free. And of course, a more, say, classical example is, of course, whenever you have a finite dimensional representation, then on the space of unitaries, you get the trace. And when you compose the trace, or rather the normalized trace, with the representation, then you get a character, right? So all these characters are, well, the first one comes from group theory, second one from ergodic theory, and the third one, say, from finite dimensional unitary representation theory. And what I want to say is that any sort of rigidity or classification results that you can obtain for characters will lead, of course, rigidity results or structure theorems for the lattice of normal subgroups or PMP actions or unitary representations. So along these lines, the first result I want to state and explain is a result about existence and classification of characters. So take a high-rank lattice. So the first item says that whenever you have a convex subset of positive definite function that is, say, gamma invariant and weak star compact, non-empty, then it contains a character. So the first item is really like a fixed point property. It's like, you know, it's like amenability, so except that amenability is for any compact set. Here it's for a very specific compact set. So in our second paper, we call this property charminability. Amenability, you know, for characters or something like that. And the second item, it's about classification. So whenever we have an extremal character, so a character that you cannot write as a non-trivial convex combination, then this character, either it's supported on the center. So if the center is trivial, it means that it's the Dirac mass. Or the unitary representation, the GNS representation, is amenable. Well, rather it's even its fundamental algebra is amenable. But anyways. But in fact, we get something more. So the second result, we get something sharper if gamma has property T, equivalently G has property T. Then we have what we call what's called character rigidity. So any extremal character is, again, either supported on the center or its GNS representation is finite dimensional. Okay? So either you get the left regular representation or you get a finite dimensional representation. And so applying this result to characters coming from normal subgroups or characters coming from ergodic theory, then you get sort of extension or strengthening of Margulis normal subgroup theorem. I want to say something important here. So the classification part items 2 and 3, actually was due to Peterson back in 2014. And actually when we started to work on this with Remy, I think it was 2017 or 2018, one of our motivations at that time was to get a better understanding of J.C. Peterson's proof. And working on this, actually, we realized that we could get more out of what we were doing. But in our paper, we obtained indeed a new proof of J.C. Peterson's results. And I should mention also that of course, the study of characters has a long history. But in this context of lattices and high-rank lattices, I guess the first result was due to Becker, who obtained character rigidity for SLDZ. And then there was the work of Peterson-Thom, extending some of Becker's result, and then also the work of Kreutz-Peterson on some lattices with dense embedding in some product groups. Okay, so this is the result about existence and classification. And you see it has two parts, 1 and 2, or rather 1 and 3, if we assume property T. Now what's interesting is when we combine the two. And so combining the two, we get something rather interesting on group sister algebras. So here, because I allow center, let me mod out by the center to get a center-free lattice, or quotient. And the first thing is that whenever you take a unitary representation, then as a straightforward corollary of the item 1 before, we get that the sister algebra generated by the unitary representation of lambda actually admits a trace, right? Because there is, on the convex set of state on the sister algebra, there is an invariant, trace, so it admits a trace. And moreover, assuming that the group has a property T, and assuming that pi is weakly mixing, it's just saying that the pi does not contain any non-trivial finite dimensional subrepresentation, then what's happening is that the left regular representation is what we call weakly contained in pi. So among all weakly mixing unitary representations, the left regular representation is like a minimum, okay? And so what does it mean to be weakly contained in pi? It's extremely concrete. It means that you have a star homomorphism, so continuous star homomorphism from C star pi to C star lambda that sends pi gamma to lambda gamma. And you see that with this homomorphism, of course, you have a trace, which is composition of the canonical trace on the reduced C star algebra with the star homomorphism. And actually, this trace is unique. So you get a unique trace. Of course, this trace might not be faithful because, after all, lambda and pi, they may not be weakly equivalent, right? So there might be, kernel for theta. But in fact, this kernel, this is the unique maximal proper ideal of the C star algebra. So it's not simple, but we can say something about the structure of, ideals. So this connects very much with the work of Becker, Cowling, Delarp from '94 when they prove C star simplicity and the unique trace property for the reduced C star algebra of these lattices. And of course, it has connections with the recent work of Kalantar-Kennedy and Breuer-Kalantar-Kennedy-Ozawa. Let me mention one more result along these lines. It's more like as a byproduct of what we are doing, but it's for topological dynamics. So again, let me mod out the lattice by its center. And let's take this time a minimal action on a compact metrizable space. Then at least one of the following things happen. So either you have an invariant probability measure on X, okay? And if you don't have an invariant probability measure on X, then actually the action is necessarily topologically free. So it means that whenever you have a non-trivial element in the group, and look at the fixed point, so this is a closed set because the group acts by homeomorphisms, and this set of fixed points has empty interior. And again, if we add, property T, if we throw property T in the assumptions, then we get something nicer. We get that we really get a dichotomy. So either the space X actually is finite, or the action is topologically free. And this in particular says that these high rank lattices, they have no no non-trivial, say, uniformly recurrent subgroups, answering a question of Glasner-Weiss. And you can view this result, for those who know, as sort of a topological analog of a result by Stuck and Zimmer from '92. So Stuck and Zimmer, for high rank lattices with property T, they showed that whenever you have an ergodic PMP action, so it's really in the measurable category, but whenever you have an ergodic PMP action, then either the space is, well, finite, or the action is essentially free, right? So it's really it's really an analog of that. So these are a sample of the sort of the applications that we can obtain. And let me say now strategy of the proof, or rather, how we arrived here. So in fact, all our main results, they will be consequences of something that we call a dynamical dichotomy result for normal, unital, completely positive gamma equivariant maps. And these maps, they will, so the source will be a von Neumann algebra endowed with an ergodic action of the lattice. And the range of the UCP map will be an abelian von Neumann algebra N infinity of G mod P. Right? And in fact, it's not hard actually to derive the main applications from this general dynamical dichotomy result, but the hard part, of course, will be to prove this this dichotomy. And you see, so far, the statement, the results, they were not involving at all von Neumann algebras. But now the proof, and now we'll talk about von Neumann algebras. And the proof of this dichotomy uses really von Neumann algebra theory. And as I said before, it actually depends heavily on whether the ambient group is simple or not. And I would say that technically and also conceptually, the proof is different in the simple case from the product case. So in the simple case, this is something that we did with Remy in 2019, and then we extended this with Uri to cover the algebraic case. And in this case, we prove actually a sharper result, something that we call the noncommutative Nevo-Zimmer theorem. And then this will be the topic of my next, the next section in my talk. And in the product case, so we get a weaker result, something that is a bit more technical to state, so I will not talk about this today. But really, we use a different method. Really, we exploit the product method. So with Remy in 2019, we handled the case SLNR, say, and at least 3, and then with Uri and Jesse, we handled the case, for instance, SL2R times SL2R. And so in that respect, these works are kind of complementary. It's not that one is more general than the other. I mean, they treat simply different cases. Okay, so let me discuss this noncommutative Nevo-Zimmer theorem. So here, and just in this section, I will assume now that D equals 1. And now we have a simple algebraic group. So take SL3Z and SL3R, if you want. And so we have this, we look at this space G mod P. So here P is what we call a minimal parabolic subgroup. And again, if G is SLN, take just the group of upper triangular matrices, okay? So we often refer to G mod P as a boundary. For the ones, for people in topological dynamics, this is the Fürstenberg boundary. For people working in measurable dynamics, we like to view this as the Fürstenberg-Poisson boundary. And so the result that was proven by Fürstenberg in 1962 for semi-simple Lie group, and then generalized much later by Beder and Shalom for algebraic group, is the following thing. So take any admissible measure on the group. Admissible measure means nice. So it means, for instance, take a probability measure which is equivalent to the Haar measure. Okay. So then there exists a unique stationary measure on G mod P. So stationary measure, it's a fixed point for the convolution operator by mu, such that the space G mod P, so the compact space G mod P, with this stationary measure, this is the Fürstenberg-Poisson boundary. So what does it mean? Concretely, it means that the space N infinity of G mod P, endowed with a G action, it's actually G equivariant isomorphic as an operator system to the space of right mu harmonic functions on the group. Okay? So because we look at right mu harmonic functions, then we have the left action. Okay? this is one possible definition of the Furstenberg-Poisson boundary. Of course, I will not go into details today, explain why this is used really in the proof, but this is to justify somehow and to give a hint about the kind of techniques that we are using, about the methods, I would say. So, the main object we look at is these UCP maps. So let's give them a name. So again, the setup is the following. So we have gamma and G a lattice, M a fundamental algebra endowed with a gamma action by automorphism. And we look at these UCP maps. So we look at UCP map. We assume that they are normal and gamma equivariant. So from M to N infinity of G mod P, let's call this a gamma boundary structure. It will become, the next slide we will see why I call this boundary structure. And also because it will appear in one of the theorem, let me denote by mult theta, the multiplicative domain on theta. This is the largest C-star algebra on which the map is multiplicative. So this framework actually it's very convenient because it's very easy to induce this structure, right? So you see you have M goes to N infinity of G mod P and then you induce. And because G mod P is a G space, when you induce G mod P, actually you get the product, G mod P times G mod gamma. And then you can integrate over G mod gamma, and then that's why you can get this induced boundary structure mapping really into L infinity of G mod P. Because in this business, to prove something about the lattice, you need to use the analysis and the geometry of the ambient group, and so you need a way to induce the problem you are looking at to the ambient simple or semi-simple group. Let me give examples of boundary structures, and let me give examples that resonate with the main applications that I have in mind, so character rigidity or say topological dynamics. So here the action of gamma on G mod P is amenable, because P is amenable, and ergodic. Okay, so let's start from a unital C-star algebra with a gamma action. Let's assume that this unital C-star algebra is separable. And because the action of gamma on G mod P is amenable, topologically amenable, and then hence amenable for any measure on G mod P. So by the way, I should say this. So G mod P, when I look at this as a Lebesgue space, it's always endowed with its unique G invariant measure class. Okay. So because the action of gamma on G mod P is amenable, then I get a measurable gamma map from G mod P to the state space of A. Right. So the state space of A, it's a weak star compact topological space, and so I get, from amenability, as a consequence of amenability, I get existence of an equivariant map. But then now I can just look at this, as an operator algebraist, and then, switch the viewpoint, and then I can look at this as a UCP map from A to L infinity of G mod P. And the formula is very natural. But remember, we want UCP map not defined on C-star algebras, but defined on fundamental algebras, right? Well, we look at the normal extension, right, on the bidual, and we cut down by the central support that will be invariant under the action, and there you go. So then you have M, which is the central corner, and restricting E double star to M, we get our so-called boundary structure. So this is one example, okay? And we can apply the above construction to two different situations. The commutative situation, where we have, gamma acting on a compact space. So we look then at the action of gamma on the space of continuous function on X. And there is the second setting where we are interested in that. And now we fix, say, a unitary representation of gamma. So now we have a non-commutative C-star algebra. And then it's, it's relevant then to look at the action of gamma just by inner automorphism, right? And then we can apply, this this construction, to both of these settings. And what I want to say now is that the next result I'm going to state, applying this to these settings, then you get fairly easily the consequences I mentioned before. Okay, so here is really the sort of the mother theorem from which we can derive our applications. So here, remember, G is a simple group, high rank simple group, and gamma is a lattice. So let's take M to be any ergodic Feynman algebra. So ergodicity of the action means that the only invariant elements are multiple scalars of the constant, yes. And let's take any boundary structure. So then we have the following dichotomy. So either the UCP map, the range, it's trivial. So then it means that on the Feynman algebra, you have, so then the UCP map, it's like a state, right? So you have an invariant state on the Feynman algebra. So this can happen, of course. But if there is no invariant state, so if the UCP map is not with trivial range, then actually its multiplicative domain is non-trivial, right? And then the multiplicative domain will be gamma isomorphic to L infinity of G mod Q for a unique Q closed subgroup between P and G. And so you see, it's so when we are not in the invariant situation, it's very surprising that we can embed in the Feynman algebra something that is abelian. But then it's very useful because, of course, in operator algebras, when we have non-commutative Feynman algebras, we don't have any points. And here we have access to points, right? So here we can exploit the action of gamma on G mod Q. That will be essentially free, by the way. And so it gives a lot of tools, actually, to prove, the results. So let me just mention a little bit of history about this. So it's called non-commutative Nevo-Zimmer theorem because in the case where M is abelian, and in the case the field is R, and actually considering G action rather than gamma action, then this is the result due to Nevo and Zimmer. So of course they didn't state it using UCP map, but they were using, they were phrasing this with the stationary states, but actually in this concept it's equivalent. And then what we did with Remy is to extend this result to non-commutative Feynman algebras, and actually to both gamma and G actions, right? And again, the statement for gamma actions follows from the statement from G actions, by inducing and then restricting. And then more recently, with Remy and Uri, we generalized the result to handle all lattices in high-rank simple algebraic groups. Okay, so this is the main result, and once again, applying this result to various UCP map or boundary maps, you can get fairly easily the main applications. So now let me turn to a more recent application, something that we realized actually fairly recently. And I want to make the connection with rigidity conjecture. Okay, so back in late 70s, Kohn showed that whenever you have an infinite group that has infinite conjugacy classes and that has property T, then the symmetric groups are of the 2-1 factor associated with lambda. It has symmetry groups that are at most countable. So by symmetry groups, I mean, for instance, outer automorphism groups and, for instance, fundamental groups of the 2-1 factor. And after these results, he conjectured that maybe the 2-1 factor L lambda should retain lambda, meaning that if we have two ICC groups with property T that give the same Feynman algebra, then they should be isomorphic. This is very ambitious. And for me, but by the way, yes, let me mention that actually very recently, It's a recent work due to Kifan, Johanna, Osin, and Sun, so from last year. So quite remarkably, they were able to construct examples of W star superrigidity, W star superrigid property ICC groups, right? So these are not the first example of W star superrigid groups, but actually they are the first that satisfy property T. And so these examples that they have are the first examples actually satisfying really rigidity conjecture formulated, like this. So here in my talk, I'm more interested in the setting of higher rank lattices. So these groups, with property T, but with many more, structure, much more structure. And I view this rather, and I compare this to the Mosto-Margulis rigidity results. So Mosto-Margulis rigidity results that actually in this setting, so high rank lattices, then abstract isomorphism of the lattice should imply isomorphism of the ambient Lie groups or algebraic groups. And so let me state the following version of rigidity conjecture, and let me a bit more, not that general, and let's stick to high rank lattices in simple real Lie groups. Okay, so let's take G1 and G2 real connected simple Lie group with trivial center and rank at least 2. And let's take two lattices, gamma 1 in G1 and gamma 2 in G2. Then the conjecture reads as follows: isomorphism of group fundamental algebra should imply isomorphism of the ambient Lie group. And in particular, it should imply equality of the rank. Okay? So this is a conjecture that I like a lot. And we didn't solve this conjecture, but we can say something that is interesting regarding the rank and fundamental algebras. Okay, so for this result, let's go back to the initial setting of high rank lattice. So, and again, we have this, we have this product, and let's take, the P to be the product of minimal parabolic subgroups. And again, we look at G mod P. So, because I allow center, once again, the center of gamma acts trivially on G mod P, so let's mod out by the center. So now we have a faithful action. And we look then at the ergodic action of lambda on G mod P. And then we can consider the group measure space fundamental algebra, so the fundamental algebra of the action. So lambda acting on G mod P. Here I'm using a slightly different notation than usual. I'm not using the cross product construction. And the result that we obtain is the following statement. So you see you have the 2-1 factor L lambda, and then it sits inside the cross product. So L lambda is a 2-1 factor. The cross product of the fundamental algebra of the action, it's an amenable type 3-1 factor. And what we show is that any fundamental algebra in between must actually come from the only obvious construction that you have, meaning that there exists a unique intermediate closed subgroup such that M is equal to the fundamental algebra of the action on the factor G mod Q. But the interesting thing is that, of course, it's well known that in each copy, in each of the algebraic group, you have 2 to the rank intermediate parabolic subgroups. And so what the theorem says is that in particular, as a corollary, we get that the rank, or the sum of the ranks, it's an invariant of the inclusion of fundamental algebras. So it gives, it gives hope to one day, get rid of the inclusion and, well, have that the rank, is an invariant of the group fundamental algebra, and for this, we need to understand better the inclusion of the 2-1 factor inside this, let's call it this non-commutative boundary. So is it possible to, out just of the 2-1 factor, construct in a canonical way this inclusion, right? Well, this is no easy task, but we'll see. But at least, I don't know, I can see some light at the end of the tunnel, but we'll see. Maybe for another time. Thank you very much.